Hello everyone and welcome to Coders of Pune. Today we're embarking on an exciting journey through Unit 5 of Computational Statistics, focusing on statistical processing. This unit is a cornerstone for anyone pursuing AIML honors, as it introduces the essential tools and techniques needed to build robust machine learning models. We'll explore everything from dimensionality reduction to feature selection, outlier detection, and balancing datasets. Whether you're new to these concepts or looking to deepen your understanding, this video will provide a comprehensive guide to statistical processing and its critical role in data science and machine learning. Statistical processing is fundamental to computational statistics. It provides the tools to prepare, understand, and optimize data for model building and extracting insights. Think of it as the bridge between raw data and powerful algorithms. By cleaning data, engineering features, and validating models, statistical processing ensures your data is reliable and your models are accurate. It also helps in handling imbalanced data, detecting outliers, and making models interpretable and generalizable. In short, statistical processing is the vital link that transforms messy, unstructured data into actionable knowledge. Statistical processing is the core of computational statistics. It covers several key points. Firstly, it's essential for data quality by cleaning up raw data. Secondly, it helps with feature engineering, using methods like PCA to create useful features. Finally, it plays a vital role in model building and validation, ensuring models are robust and perform well on new, unseen data, which is crucial for interpretability and generalizability. Imagine you have a giant toy box filled with all sorts of toys, each with many different features, color, size, material, and more. Looking at every detail for every toy can be overwhelming. Dimension reduction is like deciding to focus on just the 2 or 3 most important features, such as the type of toy and its main color. In data science, this means reducing the number of variables so that patterns become clearer and processing becomes faster. This analogy helps us understand why dimension reduction is so valuable in simplifying complex datasets. Dimension reduction offers several key benefits. First, it reduces clutter, making data easier to understand and visualize. Second, it speeds up processing, allowing computers to work more efficiently. Third, it helps computers make better decisions by focusing on the most important information and avoiding confusion from irrelevant details. By reducing the number of variables, you make your data more manageable and your models more effective. There are several popular techniques for dimension reduction. Principal component analysis (PCA) transforms data into new dimensions that capture the most variance. Linear discriminant analysis (LDA) finds combinations of features that best separate classes. Factor analysis (FA) describes variability using fewer unobserved variables. Independent component analysis (ICA) separates signals into independent components. TSNE and UMAP are nonlinear techniques great for visualizing high-dimensional data. Autoencoders use neural networks to learn efficient data representations. Each technique has its strengths and is chosen based on the data and analysis goals. Principal component analysis, or PCA, is a widely used unsupervised dimension reduction technique. Its main goal is to transform a dataset with many correlated variables into a smaller set of uncorrelated variables called principal components. This process retains as much of the original variance as possible, making the data easier to analyze and visualize. PCA is especially useful when dealing with highly correlated features, as it helps to condense complex information into a simpler, more meaningful form. Think of PCA like a satellite taking a picture of a mountainous landscape. Instead of capturing every tiny detail, the satellite focuses on the overall slope and direction of the mountains. Similarly, PCA finds the most important trends or directions in your data, condensing a complex picture into a simpler, more meaningful representation. This makes it easier to spot patterns and make decisions based on the most significant information. PCA identifies new orthogonal axes in the data space. The first principal component captures the largest possible variance, the second captures the next largest variance perpendicular to the first, and so on. By selecting only the top principal components, you reduce the dimensionality of your data without losing significant information. This process helps in visualizing high-dimensional data, reducing computational costs, and mitigating the curse of dimensionality. Imagine a scatter plot with two features, feature 1 and feature 2, showing a strong linear correlation. PCA finds the principal component that best represents the data's variance. By projecting the original data onto this new line, you transform two-dimensional data into a one-dimensional representation. This dimensionality reduction retains essential information, with the principal component capturing most of the variance from both features. Linear discriminant analysis, or LDA, is a supervised dimension reduction technique. Unlike PCA, which focuses on maximizing variance, LDA aims to find a linear combination of features that best separates two or more classes. It's particularly useful in classification problems, helping to reduce dimensionality while preserving the information that distinguishes different classes. Imagine you have a mix of apples and oranges. You want to draw a line that best separates them, making it easy to tell which is which. LDA is like finding the perfect line that puts apples on one side and oranges on the other, even if they overlap a bit. It finds the best direction to look at the data so that class differences are most obvious. LDA projects data onto a lower dimensional space that maximizes the distance between class means and minimizes the spread within each class. This creates new axes called linear discriminants optimized for class separability. The result is a simpler dataset where different classes are easier to distinguish, improving classification accuracy and reducing computational costs. For applying LDA, data points from different classes may be intermingled and hard to separate with a straight line. After LDA, the data is projected onto a new axis where classes are clearly separated. This transformation makes it much easier for classification algorithms to distinguish between classes, leading to better model performance. Feature selection is another powerful technique in statistical processing. Imagine you're trying to predict the price of a house. You have a long list of details: number of bedrooms, square footage, age, color of the front door, and more. Feature selection is like picking out only the most important details, such as square footage and location, and ignoring less relevant ones. This process simplifies your model, making it easier to interpret and often more accurate. The goal of feature selection is to identify and remove irrelevant or redundant features from your dataset. This leads to simpler models that are easier to interpret, faster to train, and often more accurate, especially when dealing with high-dimensional data. By focusing on the most relevant features, you make your models more efficient and effective. Chi-square test assesses the dependency between two categorical variables, making it a valuable tool for feature selection. It compares observed frequencies with expected frequencies to determine if there's an association. If the test shows a significant association, the feature is considered relevant and retained for modeling. Chi-square tests start by setting up two hypotheses: the null hypothesis, no association, and the alternative hypothesis, association exists. It uses a contingency table to display observed frequencies and calculates expected frequencies. The chi-square statistic measures the difference between observed and expected values. If the statistic exceeds a critical value, the null hypothesis is rejected, indicating a relevant feature. If the chi-square test leads to rejecting the null hypothesis, it means the feature is relevant to the target variable. If not, the feature may be irrelevant and can be removed. This process helps in narrowing down the list of features to those that truly impact the outcome, making your models more focused and efficient. Let's look at an example. Suppose you want to determine if contract type predicts customer churn. By setting up a contingency table and calculating expected frequencies, you can compute the chi-square statistic. If the result is significant, as in our example, it means contract type is associated with churn and should be included as a feature in your model. Steps for the chi-square test include setting hypotheses, creating a contingency table, calculating expected frequencies, computing the chi-square statistic, determining degrees of freedom, and making a decision based on the critical value or p-value. This systematic approach ensures that only statistically significant features are selected for modeling. In our customer churn example, the calculated chi-square statistic is much higher than the critical value, leading us to reject the null hypothesis. This confirms that contract type and churn are dependent, making contract type a relevant feature for prediction. Such statistical evidence strengthens your model's foundation. Variance thresholding is an unsupervised feature selection technique used to remove features with low variance. Features with little variability often provide limited information for distinguishing data points. By filtering out these features, you streamline your dataset and focus on variables that truly matter. The process begins by calculating the variance of each feature in your dataset. You then set a threshold value, and any feature with variance below this threshold is removed. This method is unsupervised, meaning it doesn't consider the target variable and focuses solely on the intrinsic properties of the features. Since variance is affected by feature scale, it's important to normalize or standardize your data before applying variance thresholding. This ensures that features with larger magnitudes don't dominate the selection process. Scaling helps create a level playing field, allowing the technique to accurately identify informative features. Features with zero variance, meaning they have the same value across all data points, offer no discriminatory power. These features are always eliminated when the threshold is set above zero. Removing such features helps in decluttering your dataset and focusing on variables that contribute to model performance. Let's consider a dataset about customer behavior on an e-commerce platform. Features include age, total purchases, browser type, gender, customer ID, and default currency. The goal is to predict repeat purchases. By calculating the variance for each feature, you can identify which ones provide meaningful information and which can be removed. For numerical features like age and total purchases, variance is calculated directly. In our example, age has a variance of 120 and total purchases has a variance of 45. Both exceed the threshold and are retained. This step ensures that only features with sufficient variability are included in the model. Categorical features like browser type and gender need to be converted into numerical format before variance calculation. This is typically done using one-hot encoding, which creates separate binary columns for each category. Once encoded, you can calculate the variance for each new feature and apply the thresholding process. After one-hot encoding, calculate the variance for each new feature. In our example, browser type and gender features have variances around 0.16 to 0.24, which are above the threshold and thus retained. The default currency feature, however, has zero variance and is removed. This step ensures that only informative categorical features are included. With a designated variance threshold, compare each feature's variance to the threshold. Features meeting or exceeding the threshold are retained, while those below are discarded. This filtering process streamlines your dataset, making it more manageable and focused on variables that truly matter for prediction. Features like customer ID, which are unique for each data point, typically have zero or negligible variance when treated numerically. These features are usually excluded from modeling, as they lack predictive utility for the target variable. Removing such identifiers helps prevent overfitting and keeps your model focused on meaningful patterns. After applying variance thresholding, features like default currency with zero variance are removed, while those with sufficient variability are retained. This process results in a cleaner, more informative dataset that enhances model performance and interpretability. By focusing on features that matter, you set the stage for more accurate predictions. Recursive Feature Elimination, or RFE, is a powerful feature selection technique. It works by recursively training a model and removing the least important features, one at a time, until only the most relevant ones remain. RFE is especially useful when you want to find the optimal subset of features for a specific predictive model. It's like building a sports team. Start with all your players, then gradually cut those who contribute the least, until you have your strongest lineup. Recursive Feature Elimination, or RFE, is a feature selection method that works by recursively eliminating features. It starts by training a model on the entire dataset and ranking features based on their importance or coefficients. It then removes the least important feature and repeats the process. This recursive cycle continues until a desired number of features is reached or the model's performance on a validation set no longer improves, effectively selecting the most relevant features for the model. Imagine you're a coach with a large pool of players. Instead of guessing who's best, you start with everyone, play a game, and see who contributes the least. You remove the weakest player, then play again, repeating the process until you have your ideal team. RFE does the same with features, iteratively removing the least useful ones, always reevaluating the team's performance. This ensures the final selection is truly the best for your model's goal. One of RFE's strengths is that it's model-specific. The features it selects are optimal for the particular model you're using, whether it's logistic regression, SVM, or random forest. This means the selected features are tailored to maximize your model's performance, not just general relevance. RFE also accounts for feature interactions, as the importance of a feature can change when others are removed. It's a dynamic, adaptive process. Let's apply RFE to a real-world scenario, predicting whether a customer will default on a loan. The bank's dataset includes features like credit score, annual income, loan amount, employment length, debt-income ratio, number of open accounts, purpose of loan, home ownership, marital status, and number of dependents. The goal is to select the most impactful features for building a robust prediction model. For applying RFE, categorical features like purpose of loan, home ownership, and marital status are converted to numerical variables using one-hot encoding. This ensures all features are in a suitable format for the model. For this example, let's use logistic regression, known for its interpretability and clear feature coefficients. We'll aim to reduce the feature set to the 5 most important predictors. The first iteration, the logistic regression model, is trained on all features. The model assigns coefficients to each feature, indicating its impact on predicting loan default. For example, credit score might have a coefficient of 0.8, annual income 0.5, and so on. The feature with the smallest absolute coefficient, say marital status divorced, is identified as the least important and removed from the dataset. With one feature removed, the model is retrained on the remaining set. New coefficients are calculated and the next least important feature, perhaps marital status single, is identified and eliminated. This process continues with the model always adapting to the current set of features, ensuring that the most relevant predictors are retained. After several iterations, features like marital status, number of dependents, and less impactful home ownership or loan purpose categories are removed. Eventually, the process leaves us with the 5 most influential features: credit score, annual income, loan amount, employment length, and debt-to-income ratio. These are the variables that matter most for predicting loan default in this scenario. By applying RFE, the bank now has a streamlined, efficient predictive model. Using only the most relevant features reduces computational complexity and can even improve model performance. The specific features selected depend on the data and model, but the process ensures that only the most impactful variables are used for prediction. Next, let's talk about outlier or anomaly detection. This process identifies data points that deviate significantly from the majority. Anomalies can signal underlying problems, rare events, or even new discoveries. For example, a sudden spike in credit card transactions might indicate fraud, while an unusual sensor reading could point to system failure. Detecting these outliers is crucial for maintaining data integrity and uncovering important insights. Types of anomalies. 1-point anomalies, global anomalies. These are individual data points that significantly deviate from the norm, such as an unusually high credit card transaction. 2. Contextual anomalies, conditional anomalies. These data points are anomalous only within a specific context. For example, a temperature of 30 degrees C is normal in a desert but anomalous in Antarctica. 3. Collective anomalies. This involves a collection of interconnected data points that, when observed together, represent an anomaly, even if each individual point seems normal in isolation. An example is a series of small, repeated credit card transactions that may indicate fraudulent activity. Statistical methods are a classic way to detect outliers. The z-score method measures how many standard deviations a data point is from the mean. Anything beyond +3, or is often considered an outlier. The interquartile range IQR method defines a normal range based on the middle 50% of data, flagging points outside this range. Grubb's test is a formal statistical test for identifying a single outlier in normally distributed data. These methods are simple yet effective for many datasets. Imagine a student who scores 3 standard deviations above the class average on a test. That student is an outlier, just like a data point with a high z-score. This analogy helps us understand why extreme values are flagged. They're rare and may indicate something unusual or important that deserves attention. Think of the IQR method as setting up fences around the middle 50% of your data. Anyone outside those fences is considered an outlier. This approach is robust to extreme values and works well even when data isn't normally distributed. It's like checking who's inside or outside the main crowd at a party. Those far from the group stand out. Machine learning methods use algorithms to identify anomalies. Supervised methods like classification algorithms require labeled data to distinguish between normal and anomalous instances. Unsupervised methods, which are more common since anomalies are often unlabeled, don't need labeled data. Examples include one-class SVM, which defines a boundary for normal data, isolation forest, which isolates anomalies using decision trees, autoencoders, which identify anomalies by high reconstruction errors, and clustering-based methods, which flag points that don't belong to a cluster or form small clusters. Proximity-based methods detect anomalies based on their distance or density relative to their neighbors. The local outlier factor (LOF) measures the local density deviation of a data point, flagging a point with significantly lower density than its neighbors as an outlier. An analogy is a person alone in an empty parking lot being an outlier compared to a dense crowd. K-nearest neighbors (KNN) identifies anomalies as points whose k-nearest neighbors are far away. Now let's address the problem of imbalanced data. In many classification tasks, one class is much more frequent than the other. Think of fraud detection, where fraudulent transactions are rare. If you train a model on this data, it might always predict the majority class, missing the minority cases that matter most. Resampling techniques help balance the dataset, ensuring the model learns to recognize both classes. Random undersampling is the simplest way to balance classes. It involves randomly removing samples from the majority class until it matches the size of the minority class. For example, if you have 1 million non-fraudulent transactions and 1,000 fraudulent ones, you randomly select 1,000 non-fraudulent transactions to match. The result is a smaller, balanced dataset that can help the model focus on both classes. Imagine you're baking a cake, but your recipe calls for 10 cups of flour and only 1 teaspoon of sugar. The result would be mostly flour. Undersampling is like reducing the flour to match the sugar so your cake is balanced. In data science, this means reducing the majority class to match the minority, ensuring fair representation. Undersampling can improve a model's performance on the minority class and speed up training by reducing dataset size. However, it comes with a trade-off. You're throwing away valuable data from the majority class, which might contain important information. It's a quick fix, but not always the best solution for every problem. Random oversampling takes the opposite approach. Instead of removing data from the majority class, it replicates data from the minority class until both classes are balanced. For example, you'd make copies of the 1,000 fraudulent transactions until you have 1 million, matching the non-fraudulent ones. This creates a larger, balanced dataset without losing any original data. Think back to our cake analogy. Oversampling is like adding more sugar until it matches the amount of flour. Now, your cake is balanced, but you might end up with a very sweet result. In data science, this means duplicating minority class samples, which can help balance the data but may also lead to overfitting. Oversampling ensures no data is lost and can effectively balance classes, improving model performance. However, by simply copying existing data points, the model might become too good at recognizing those specific examples, leading to overfitting. It's like a student who memorizes answers but struggles with new questions. Often the best solution is to combine undersampling and oversampling. For example, you might reduce the majority class to 500,000 and increase the minority class to 500,000, creating a balanced dataset without excessive duplication or data loss. More advanced techniques like SMOT generate synthetic data points for the minority class, further reducing the risk of overfitting. SMOT, or synthetic minority oversampling technique, creates new, synthetic data points for the minority class instead of just copying existing ones. This helps the model learn more general patterns and reduces the risk of overfitting. SMOT is widely used in imbalanced classification problems and is a powerful addition to your data preprocessing toolkit. Dimension reduction simplifies high-dimensional data by reducing variables while keeping crucial info. ECA, unsupervised, transforms data into uncorrelated principal components, maximizes variance. LDA, supervised, finds combinations that maximize class separation. Feature selection directly selects the most relevant original features, eliminating redundant ones for simpler models. I-square assesses dependency between categorical features and the target. RFE recursively eliminates the least important features based on model performance. Definition: anomaly detection identifies data points that significantly deviate from the expected pattern, indicating rare events like fraud or failures. Types of anomalies: we look for point anomalies, single extreme points, contextual anomalies unusual within a specific context, and collective anomalies, groups of points that are suspicious when viewed together. Detection methods: simple statistical methods like z-score and IQR are often used. Advanced techniques include machine learning methods like one-class SVM and isolation forest, which learn the boundaries of normal data. Proximity-based methods like LOF, local outlier factor, and KNN find anomalies based on their distance or low density relative to their neighbors. Problem in classification: when one class is far more frequent, e.g. 99% non-fraud, 1% fraud, models become biased, failing to predict the important minority class. Techniques to balance classes. Random undersampling randomly discards samples from the majority class to balance counts. Trade-off: faster training but risks loss of valuable information. Random oversampling replicates samples from the minority class to increase its size. Trade-off: no data loss but risks overfitting due to exact copies. Advanced sampling, e.g. SMOTE, creates new synthetic data points for the minority class to mitigate overfitting risks associated with simple replication. Statistical processing is the link. It is the essential step between raw data and effective computational algorithms. Goal: to ensure data is optimized for accurate, reliable, and efficient model building. The toolkit mastering these techniques is crucial for robust AI/ML applications. 1. Preparation: quality understanding, cleaning data, and understanding distributions. 2. Refinement: features, dimension reduction, and feature selection. 3. Safety and fairness: integrity bias, outlier detection, and resampling. Congratulations, you now have a comprehensive understanding of key statistical processing techniques for AI and machine learning. From dimension reduction and feature selection to outlier detection and resampling, these methods are the foundation of robust, reliable models. Apply them thoughtfully and you'll be well on your way to data science mastery. Thanks for watching. We've covered the core of statistical processing for your SPPU TE Computer Engineering syllabus, Unit 5. If you found this lecture on dimensionality reduction, feature selection, and resampling helpful, please give it a thumbs up and subscribe to Coders of Pune for more university-level content. Feel free to drop your questions about PCA, outliers, or any other topic from this unit in the comments below. See you in the next video. Happy coding!